We'll begin like we did in free vibration with the simpler case when we have an undamped system. So we're going to focus on 1 degree of freedom undamped systems with simple harmonic forcing acting upon it. When we get to our identify step, we want to see what does the equation of motion for a system like this look like. So as we saw before in free vibration, our left-hand side will have an mx double dot and a kx. We'll have no x dot term, signifying that this is an undamped system. But now we look at the right-hand side, and we have some amplitude f naught times a cosine omega t function. The left-hand side has our one dependent variable and its derivatives x, and now our right-hand side is non-zero, signifying that we do have forcing, but we see it's in the form of some constant times a cosine omega t function, where omega is going to be the driving frequency. So our right-hand side has an explicit function of time, where our left-hand side has x, which is also a function of time, but our dependent variable. To make the identification of parameters simpler, we can rewrite our equation of motion by really dividing through by the mass term, and we can get x double dot plus our natural frequency squared times x equals this amplitude over m cosine omega t. We want to pay attention here. Omega n is the natural frequency of our system. It does not depend on the forcing, it just depends on how our system is linked together, as we'll revisit in a moment, and simply omega is what we call the driving frequency. It's the frequency at which our force is being applied. Now we want to go about solving our equation of motion once we can identify the type of system we have. Well, we have on our left-hand side this ordinary differential equation, x and x double dot, but now our right side is not zero anymore. This is now not a homogeneous equation. So how do we solve an ordinary differential equation like this? Well, if you recall back to your ODE class, we actually start with the homogeneous solution. So what we do once we're in this standard form, like we see up here, we are going to solve it for when the right-hand side is zero first, and that's the homogeneous solution. Now, we actually already did this because this is what the previous section was all about. In free vibration, everything was already the homogeneous. So we saw that that solution started in the form of this cosine term plus this sine term. And we had this currently unknown coefficient C1 and C2. In the previous section, I did rearrange this and rewrite it a little bit, where I wrote it as that single cosine term with an unknown amplitude and an unknown phase. Here, I'm actually going to leave it back in this original form for our homogeneous solution. So notice in the homogeneous solution, these oscillations are taking place at the natural frequency omega n. So we don't know C1 and C2 yet, but at this point we cannot apply our initial conditions and solve for C1 and C2. We need to wait for the total solution. So they're going to impact the total solution, not only the homogeneous. The total solution is going to be the homogeneous part plus the particular solution that we need to find. So the particular solution, if you remember, is going to depend on what the forcing looks like, what does the right-hand side of our ODE look like, and what's the form of the left-hand side of our equation. In this case, where we don't have damping and our right-hand side is just a simple cosine function, we can assume that the particular solution is also a cosine function at the same driving frequency omega with an unknown amplitude x. And if you recall, the homogeneous solution alone does solve the system when it's equal to zero, and the particular solution also will solve the system, but the total is when we superimpose them together to get the full solution for the oscillations in our system. So what we need to do first is find what is the amplitude of that particular solution. So what we do is we can take that assumed form and we can put it back into our ordinary differential equation and see what x must be that's going to satisfy the equation. And if we do that, we're going to get the x in 3 different ways we can write it here, but they're all equivalent to each other. So putting it back into our equation, putting this x cosine omega t back up into here for our x and our x double dot, we're able to solve for the value of x that satisfies that equation. And then this again is what we get out here. So the amplitude over m times the difference of the natural frequency and the driving frequency times the sum of the natural frequency and the driving frequency. Or this middle term here, we can express it as well. I have like the middle way of looking at it here because we can see that in the denominator we have this ratio of the driving frequency to the natural frequency, and that's going to come into play as we analyze what some of these solutions look like. So putting the particular solution back into our ODE, that's how we get the amplitude of the particular solution to look like this. Now that we know the x value, we can put our initial conditions into our total solution. And we're going to get that our total solution looks like this. I won't go into the details, the algebraic details of getting this, but if we apply our two initial conditions saying that our initial position is x naught, the initial velocity is x dot naught, then this is what we get out with the total solution. Keep in mind that we do know the value of x. I'm just writing it in a more short form down here, where we can now put in the x we now know, the x naught, and the x naught dot that we know. Now, in some special cases, we can look at our system and we can start it from rest. For this instance, when I'm talking about starting from rest, I'm saying that our initial position is 0 and our initial velocity is 0, not only the initial velocity being 0. So our system is starting at 0 initial conditions, and then we start our forcing function. We start that cosine term. So what's going to happen is this middle term is going to drop out and go to 0, and then this x0 is also going to go away because it's equal to 0. So we're going to be left with this shorter form here. The x of t is going to be our amplitude times the difference of cosine omega t minus cosine omega nt. So notice here in our solution, because we have no dissipation in our system, this x of t is going to be oscillating at two frequencies, the driving frequency omega and the natural frequency omega n. When we talk about damping in the next subsection, we're going to want to keep in mind that at steady state, or as time starts to get larger and larger, the natural frequency term is going to drop out and the system will be oscillating just at the driving frequency. That's not the case in the undamped system. It will be oscillating at these two frequencies. So this was the case when our forcing function was a cosine function. This is what the total solution looked like up here. And then in the special case, we saw that when we started from rest, 0 initial conditions, it simplified down to these oscillations. But another case we can have, and it's going to look pretty similar to what we just saw, it's just a little bit different, is the case where our equation of motion, the left-hand side looks exactly the same, but our forcing function is a sine. Really the difference is going to be what is the force when time equals 0. With a sine function, it's going to initially have 0 force acting on it when the timer is at 0. And with a cosine, it's going to have maximum force acting when the timer is 0. And the solution to it will look slightly different. So we can rewrite it, again, going to look basically the same. The homogeneous solution is unchanged because the left-hand side is what determines the homogeneous solution. And the particular solution is going to be in the form of x sine omega t because that's what the right-hand side looks like. Again, this is an undamped system. In the next subsection, when we looked at damped systems, the particular solution we're going to see has a sine term and a cosine term. But what happens is we're going to put this particular solution in for x and x dot, and then we're going to be able to solve for x, just like we did before, and actually the result is going to be identical for what the value of x is. Then we can apply our initial conditions and get our total solution. And you'll see that does look a little bit different than what we saw when cosine was our forcing function. It's a very similar format. We have a sine term, a cosine term with our natural frequency, and now a sine term with our driving frequency, but the coefficients are different in front of the sine term and the cosine term. And when we start this system from rest, 0 initial conditions, that is to say, then it's going to simplify down to this expression. Not quite as elegant and short as we saw for the cosine term, but still similar, that it's going to be oscillating at the driving frequency omega and the natural frequency omega n. So those are the two cases we could see when we have a simple harmonic forcing acting on it, where it's just one cosine term at driving frequency on the right-hand side, or a sine term on the right-hand side at that driving frequency. But now let's focus in on this amplification term, this x term that we are going to have involved in our system. So what does it do as we change what the driving frequency in our system is? So I'm going to use that middle definition from the other slide, and I want to divide through by f naught. So this amplification is here telling me the ratio of my output amplitude to the input amplitude. And what we see happening here is we have this 1 over k, and then the denominator we have this 1 minus omega over omega n squared term. So it's really this omega over omega n that's going to be having an effect on the size of this ratio. So what happens as we modify that input or that driving frequency? So what happens if our omega value is small? So if we have a low input frequency, we're going to see that there is little amplification. So what's happening here, if we can let this omega value get really small, we're going to have 1 minus a really small number. So that's going to leave us with just 1 times a k. So if we see what happens in the limit as omega goes to 0, this ratio is going to go to 1 over k. So low frequencies in these 1 degree of freedom systems gives us little amplification. So now what happens if we have a high driving frequency? Well, we're going to see that here this ratio of omega over omega n is going to get really, really large as omega gets really large. So we're going to have 1 minus a really large number is going to be a really large negative number. So what happens when the limit of omega goes to infinity is we're going to have 1 over k times a really large negative number. Well, k is some finite value, so it's going to be 1 over a really large negative number. 1 over a really big number that's negative is going to give us a really, really small negative number. And that's what this is signifying here, this negative epsilon. Epsilon is just a really tiny number. So that ratio will get smaller and smaller and smaller, and it's going to be an antiphase, meaning when the maximum force is being applied, we're going to be at the minimum position and vice versa in these oscillations. So high frequencies will give us a very attenuated output amplitude and will be an antiphase with the input. And finally, what happens if our driving frequency is near our natural frequency? We're going to see that the amplification becomes very large. So again, looking at here, if omega is very, very close to omega n, we're going to have this ratio is going to be a number very close to 1. 1 minus a number very close to 1 is going to give us just a very small number, because it could be like, this number could be 0.99999. 1 minus that number is going to give us a really small decimal. So what's going to happen is we're going to have 1 over a really small number in the denominator. 1 over a really small number is going to give us a very large number. But it's also going to depend, is the driving frequency a little bit less than the natural frequency, or is it a little bit greater? So we can look at these two limits and see what happens. If omega is a little bit less than the natural frequency, so the limit as we approach it from the left, we're going to get that this ratio goes towards a positive infinity. We're going to have a very high amplitude in phase with the input. Alternatively, if our omega, if our driving frequency is a little bit larger than our natural frequency, so it approaches it from the right-hand side, then we're going to have 1 minus a number that's a little bit bigger than 1 is negative, and we're going to see that this ratio is going to approach negative infinity, meaning that the output amplitude will be in antiphase with the input amplitude. The maximum of the forcing will coincide with the minimum of the position, and vice versa. Now, what does all this look like where we're studying an amplitude of our system and varying the input frequency or the driving frequency into the system? This is the basic premise from what we saw in system dynamics when we were looking at the Bode diagram. How did the driving frequency influence that ratio of our output amplitude to our input amplitude? And this is the type of pattern that we saw in our 1 degree of freedom systems. Low frequency basically had no amplitude increase or decrease, it was more or less flat. Near the natural frequency, we saw a spike where the output got very large. And as we got to higher and higher frequencies, we were seeing that that amplitude got smaller and smaller. And that's the same trend we're seeing here, but completely in this time domain and coming from this analytically derived expression for the output.